the claim that I'm going to make in this talk, along with other things that I'm going to introduce, is that advanced cryptography, like zero-knowledge cryptography, can allow us to use cryptography that already exists in existing systems to both reclaim our data and protect our anonymity. Sweet. So I'll be talking primarily today mostly about ZK email and kind of how I think about modern cryptographic relating. And ZK email has a lot of teammates, so while I'll be talking about everything, most of these things are work that we've done in collaboration with many, many folks. Sweet. So I'll start talking mostly about like what is ZK, how does it work, how does something like ZK email work. A couple of I'll narrow down on a couple of really interesting use cases like whistleblowing, and then we'll switch gears a little bit and talk a little about how you actually verify these public keys and how you get old public keys. And then I'll leave some notes about the future, other ways we can use ZK, and open source development and things like that. Sweet. So starting with what is ZK, I imagine most people in this room are probably not super familiar with how these proof systems work. So one very simple example, which will help illustrate, okay, like what does zero-knowledge cryptography give you, is imagine I have like a deck of cards in front of me, and they're all face down, and now I draw one out, and only I see it, and it's like a 7 of hearts. And now I want to prove to you that I have a red card, but I don't want to tell you it's the 7 of hearts. How might I do this? Like physically, you don't have to use any weird mathematical things. I'll let people think for yeah. Yeah, exactly. So I could like put a big piece of paper on top of it and cut a little hole in the paper, and then put it on top of like one of the red pixels on the card, and then turn it around. And now you know I have the card, and you know it's red, but you don't know which red card it is. And so that's kind of one example of selective disclosure. Another thing I could have done to prove that could have been I could have turned over the 26 black cards remaining in the deck. And now you know, oh look, I've learned nothing about which red card he has, but I know he must have a red card. So this is a very simple, intuitive way to intuit, okay, like how can you get selective disclosure from a ZK system? But if you want to use this for more interesting things, you need to define more key primitives. So what most ZK proof systems do is they do a kind of similar selective disclosure thing, but they do it for arithmetic operations. So they'll say something like, I want to prove to you that A plus B equals C, but I'm going to hide A and B and only reveal to you C. In isolation, this is not that interesting, but when you combine it with multiplication, where I can prove to you x times y equals z, and I know some x and I know some y, and you'll see z as well, but I'm going to hide x and y. Now you have enough to build like a Turing machine, and you can build any function that you can imagine. And in reality, when you want to implement these, you often have to rely on very complicated, more complex cryptographic techniques like discrete log, polynomial commitments, pairing-friendly curves, hashing. I'm happy to do like a tutorial during the break or do like a 30-minute deep dive and I explain how to build a ZK proof system from scratch, but I didn't think that would be a great fit for the talk. But if you take this at my word that you can build an addition and multiplication, and there's like dozens and dozens of papers of different schemes to construct this, then you can build the most simple and interesting cryptographic primitive you can build with this is a hash. So you put a hash and you break down the hash into additions and multiplications, and now you encode it as a ZK proof. So now the kind of end result of this hash is I can prove to you, look, here's the hash of some data. And I can prove to you I know the preimage of the hash. Like I know the raw data that went into that, but I'm not going to tell you what it is. And like the kind of simplest version you can use this for is like a kind of a ZK password authentication system, where look, I know the password whose hash is in your database. But you can use it for much more interesting things, and I'll show you that later as well. And the kind of second key thing you can construct with these additions and multiplications is a cryptographic signature. So most cryptographic signatures are the idea that you can take a secret key and a public key and a message, and then you can use the secret key on the message to construct a signature. And now anybody who sees the message and your signature can verify it and say, yes, the owner of that public key in fact signed that message. So concretely, why is this useful for emails? Where does emails come into here? So every email you sent or received since 2017, and even some from before then, are signed according to the DKIM protocol. This is like a spec which is used for spam prevention primarily, in which all of the emails that an email server sends are signed with an RSA signature of the hash of the email. So basically what the sending mail server will do, will say, okay, I'm going to hash the from, the to, the subject, your body hash, And then I'm going to sign that with my private key. So maybe Gmail will be like, oh yes, you're signed into Gmail. I'm going to use Gmail's private key, and I'm going to sign that you in fact sent this message. And now the recipient on their end is going to verify, yes, this was sent from Gmail. OK, this looks legitimate. I'll show it to the user, and I'm not going to spam block it. And so what you can do is you can imagine what if you put this whole verification into a ZK proof. So now I can prove to you that I received some email. And by decomposing the RSA and SHA and all these things into more simple arithmetic pieces, and we also wrote regex inside a ZK proof, you can now prove that I received some email, and I'm only going to reveal a part of it. And you can verify the public key on DNS. So for instance, Gmail will host their public key on like something.gmail.com. Cool. So OK, concretely, like what properties does this unlock? And then I'll dive a little bit into specifics. So one of the things we like to call this is like programmably provenant data, in the sense that you can verify the data directly from a user's sending mail server. Like, if I've received an email from somebody, I don't need to trust that, oh, some third-party NPC or some third party has verified this and I need to trust them. I can directly say, yes, like here is a ZK proof that contains that proves that that public key of the sender in fact sent that message. You can extract data arbitrarily and programmably. You can say, look, I only want to reveal the from address, or I only want to reveal the to address, or I only want to reveal my domain, whatever it is. And then you can move around this data to other services. So if I give this proof to somebody, they can give it to somebody else. And so, OK, what are like some things you can build with this? You can imagine that, for instance, I can prove one very basic example of this is I can prove I own, say, a Twitter username. Normally, you would have to like have an API key and query into someone's Twitter, have them log in, come back. But here, I, kind of asynchronously, can prove I own a Twitter account by proving I got an email, say, asking me to password reset my Twitter account, which only the owner can get. I could also use any notification emails. And I can prove I own this Twitter username, or this GitHub username, or whatever other username is tied to my email. That's kind of interesting, and one of the folks we've worked with basically uses this for like AI training data compensation. They basically say, look, like we don't want people to scrape our data without our consent, and so we are going to prove that we own this Reddit handle, and then we're going to provide our data, and that way we can get directly paid for that data instead of Reddit's API getting paid for all the content that we created. Similarly, you can prove, for instance, you got a KYC email from Airbnb. So now that I've KYC'd on one service, I can just prove I got the confirmation email and then reuse that KYC everywhere else. And you can see a bunch more projects if you scan this QR code. Cool. By the way, I should pause if anybody has any questions about how this works, because the rest of this presentation kind of relies on having a decent understanding of what the ZKML proof is actually doing. Then we kind of have any questions before we move to more applications. Cool. OK. OK, so another cool email you can do, and an example of something you can do with this, is you can verify payment emails. So for instance, here I've received a payment email from somebody, and now I can prove that I sent or received a transaction, like money to or from them. And now you can bridge between any two payment services that send you kind of emails, payment confirmation emails that have enough information. So you can imagine that I can take, say, Venmo, which only works in the US, and HDFC Bank, which only works in India, and now I can transfer money, like rupees on HDFC to somebody, and that person can transfer me Venmo money to, say, a liquidity provider or to me directly. And now two people in two totally different countries using two totally different payment services can directly transact without any intermediary. And this organization called ZKP2P.XYZ built exactly this. And they've done like over now $100,000 in volume of these exact kind of trades where you use like ZK email proofs to authenticate that they happened. And so there's no kind of middle party. And one very cool thing that they just released is that you can imagine you can build arbitrary marketplaces on top of anything that you get payment confirmation emails for. So concretely, whenever you transfer a domain on Namecheap from one person to another person, you get a confirmation email. Now you can imagine you just build the exact same system off of this, where you say, look, I'm going to prove to you I transfer you to the domain, and now with no centralized third party, I can now say send money the other way automatically. And so I can say, look, like I'm going to now build arbitrary marketplaces on top of these confirmation emails I'm receiving. And you can try this out live if you want. You can go to zkp2p.xyz and you can literally buy a domain, say from Namecheap, without ever having, and do the payment without relying on any trusted third party. And people have built lots of interesting stuff on top of this, such as like communication. So these folks at Tonk basically said, look, we're going to prove that you are a specific kind of person by proving you have a specific kind of email in your inbox. And that's going to gate your access to some sort of group chat. And okay, this is one interesting example. So I saw in the Discord for this event, to verify that you have a ticket to this conference, you have to send your little code. And then Boris has to read it, be like, yes, this code in fact corresponds to that person. I did in fact issue this ticket. And then he'll let you into a gated server. But what you can do is you can do this with a ZK email proof. So this morning I spent 2 minutes and I basically went to this website we have, stk.prove.email, and I specified, okay, I want to now make an email proof that I received a ticket for the Causal Islands 2024 conference. And it's super simple. All you have to define is that I got an email from Tito.io, which is a ticketing service that Causal Islands uses. And then I say, look, in the subject, I want to make sure it says your something and then ticket. And then I'm going to make that something public so you know which conference I got the ticket for. And it better say Causal Islands 2024. And it's super simple. This definition only took me about 2 minutes to make in the SDK. And if you see it, I can kind of transfer here. And you can literally try it out. You can log in with Google, and you can select. So if I log in now with my email, second. So you can imagine here I'm signing with my email, but if you're not comfortable signing with your email, you could also just drag in the raw email file. I can just select, yep, I want to prove that I got this email, and I'm not going to hide the specific person I am, so nobody's going to know that I am ayush@gmail.com or whatever, but they're going to know that I have some email which shows that I have a ticket to this event. And now I can create a proof, and I made one earlier this morning that's completed, but you also can just go to this website, stk.prove.email, and literally make this proof right now and prove that you have a ticket to this event, which I thought was pretty cool. So now you can build it into Discord, and now Boris doesn't have to individually verify each person has been to this, has a ticket to this conference. Sweet. Okay, so before we move on to the whistleblowing case, I'll also pause in case people have questions about any of these things. Sweet. Oh, yeah. Is there a question?
How does the trust bit work here? So I receive an email, and because it's already signed by DKIM, then I can select. Then I can construct another proof that says I received this email from that person, and the contents of the email. I can't cheat. I can't change the email or anything like that.
Exactly. So the idea is that in any email you've received has something like this. This is if you actually view the raw email specifically for the Causal Island ticket email, you'll see something like this, which basically says, look, we're going to sign this email with RSH.56, and it's going to have all these fields, the date, the from, the to, whatever. And this is the signature. And that signature better match one-to-one with your characters. If you change a single character, the signature is no longer going to match. And so what we say inside the ZK proof is now, effectively the statement you're making is the ticketing service, their email server signed a message saying they in fact sent that email, and you are proving that you have such a signed message, but you're hiding all the information you don't want to reveal. Yeah, another question. Oh.
And so in this case, you know which email address got the ticket, but then when you share that on Discord, I mean, how do you know that they have the email address? I don't understand that part.
Yeah, so the idea is that the thing you would actually be sharing on Discord would effectively be something that looks like this proof. And so you'd imagine, you put this into a QR code, but this is kind of just a bunch of elliptic curve points, where if you do what's called a pairing operation on it, then you can verify that in fact this proof shows that I have a ticket to this event. And somebody can go in and we have a bunch of tools that you can use to verify, yep, these random elliptic curve points correspond to this statement that I have a ticket to this. But the idea is that you could kind of say encode this as a QR code, put it into the Discord. Now Boris can scan it and say, yep, this looks like a unique ticket. I've not seen this before, and I'm not going to learn their email address. I'm just going to learn they have this email with a ticket. And from just scanning that QR code and running the verification process locally, they can let you into the server. It's a good question. Okay, so once somebody has put a proof in the Discord, why can't everybody just copy paste that? Yeah, it's a great question. So in this proof, we also include this thing called a nullifier. I've not described it, but the idea is that you will also publish an additional value which is unique per email but doesn't reveal your identity. So one example of this is I can publish, say, the hash of the DKIM signature. And then now that hash is kind of this random string, doesn't tell you anything, but you can't make a second proof of the same email. Because when Boris scans it, he's going to see that hash and it's going to say, yep, this thing has already been scanned before. And so you'll know, okay, you keep a list of, okay, here are the unique public values, and those can't be changed. Yeah, but it's fair enough. Yeah.
Have you thought about use cases, situations where a user can have arbitrary input into an email? For example, if I go to help desk of a website and I insert my ticket, and in a ticket I'll type arbitrary text where like you received this ticket to this number, my name, blah blah blah, stuff like that, and it will match the regex. How do you deal with this?
Yeah, so great question. So how do we protect against like user inputted emails or something? And so the idea is you have to be quite careful. So you have to make sure that the emails you're processing have like a limited scope for user input. So for instance, like in the Venmo email, the only thing you're allowed to the only thing users can actually manipulate is like the message of the transaction, the amount of the transaction, and like the sender and recipient name. But the format of the email other than that is kind of set. And so if you kind of have to be careful when you're proving this email, okay, the user cannot go in and manipulate too many fields. But usually there'll be some like HTML div that you can't insert or else it will be escaped. And you basically say, oh, like we're going to expose that div. And for things like the subject or the from or the to, we have a bunch of robust parsing logic that makes sure that there's no way to get around that. Because there's specific characters that can only be inserted by a mail server and not by a user. But yeah, it's a great question. Like, you have to be a little bit careful to make sure if you're going to parse an email body that the user couldn't have inputted that.
So I guess in this setup, you trust the email providers to only sign emails that you've actually received. So do you have a list of like reputable email providers that you trust to do this, or how does that work?
Yeah, so I'll go over that in the third section, the archive. But basically the idea is that, yeah, like you need, because this kind of relies on the email having a public key, you are relying on the fact that, yes, that email server, in fact, authenticated that person, sent that email, and then sent it to me. And so if something like Gmail, it's like, yeah, like, okay, we have to trust Gmail to have to authenticate that user and then send the email. But anyways, you trust your email provider, right? When you receive all the emails in your inbox, because this whole DKIM spam filtering thing is happening, you are trusting inherently that those email senders have sent those emails. Right, exactly. So like for instance, for the ticket thing, for instance, we are trusting that like the ticket provider Tito.io is not going to go in and sign some malicious email and send it out, or else they could kind of get around the system. So you're sort of relying on the sending mail server to act honestly. But in many cases, that's sort of like it's kind of like the requirement you have anyways, right? Like if your ticketing service were to like manipulate and try to fake tickets, then what was the point of using them as your ticketing service? So
what if everyone lied?
Yeah. Sweet. Let's pause there. Yeah, we'll keep going and we'll save more questions till the end. Sweet. Okay, so whistleblowing is a very interesting use case because anonymity here is super critical. There are cases, for instance, Edward Snowden or WikiLeaks type cases in which because somebody's anonymity was leaked by the source verifying who they were, they went to jail. And this happened like for in many cases. This is one such a very high profile case where because her like whistleblower identity was leaked, she like went to jail. And so you can imagine now with ZK email, you can mask the stuff you don't want to reveal. So you can say, I am a whistleblower in this organization, and I'm going to leak this email showing some information, but I'm going to hide all of my personal data. And so you can kind of go in and mask that stuff yourself, and then publish a ZK proof of that email. And now journalists, instead of having to verify, oh yeah, you are that specific person, that specific organization, you can verify, oh yeah, the email chain of provenance is true, and I don't have to verify exactly who you are as a person, which can be very powerful for releasing interesting new kinds of truths into this world. And you can imagine now you can build like broad whistleblowing forums. So something like Blind or Glassdoor is kind of built around a less strong trust assumption where Blind or Glassdoor knows who you are, and then they kind of just hide in the UI. Okay, like we're not going to reveal where exactly this came from. But you can imagine now you have this in a completely private way where even the hosting website has no clue who you are. They just know you have like an @openai.com domain or an @boeing.com domain or whatever, and therefore you work there, and now you can say something on behalf of those companies, which could be very spicy. And folks have built versions of these platforms. You can try them out, and we're kind of still iterating on, okay, how do we make sure that like there's upvoting and downvoting so we don't show like super toxic content all the time. But this kind of stuff is already live, and we're excited for people to keep experimenting with it. Okay, so how concretely do you do this, like own an @something something domain? So one way you could do this without even using emails in your inbox, but by using your login tokens, is that when you log into a website, you will often be issued a JSON web token. This is basically a digital signature saying, yep, you in fact signed into that website, and your login button, whether it was like login with Gmail or whatever, is going to sign a message that looks very similar to the email DK message that you can verify with exactly the same kind of ZK email proof. So we can go through a few ways of doing this. Now imagine on that website you have a little Google sign-in button. The person signs in with Google, and now they generate a ZK proof of the JWT, and now they use it. Now the problem is Google has server logs of who logged in through that app. And so if you posted something super critical, they could go back, cooperate with law enforcement or whatever, and then dox you. So how can you do this without Google having a log of all the sign-ins to that website? Well, you could imagine that you could allow tech-savvy users to overwrite the Google Apps OAuth ID and secret with their own. So now you have no idea which Google app authorized your login. You could use any Google app in the world, any sign in with Google button on any website, and make a ZK proof of that. Well, the problem is they can still kind of trace the originating IPs, and they know where it's coming from. They know, oh, you signed in. You still used the like login button on the whistleblowing website or whatever. But it turns out you don't have to use just like Google OAuth keys or whatever. You can use any sign-in JWT from any website. So I could even go to like, I don't know, chatgpt.com, take my login, take that JWT from that website, and then prove that, yep, ChatGPT verified I logged in and owned this email, and now nobody can trace my login because I'm going to use a JWT from a totally random website on a totally random device of mine. And this is kind of the scale of things that these apps do. So the Stealth Note app over there does the JWT via Google Sign-In, and the Nosy app does it via arbitrary JWTs from arbitrary websites. In this case, it's specifically shipped with like ChatGPT. Sweet. Okay, so I've already spewed like tons of these interesting use cases at you, but one kind of detail that we've missed is, which you kind of alluded to earlier, is how do you actually verify these public keys? Because services will rotate these public keys maybe every 6 to 12 months or so. So for instance, Gmail every 6 to 12 months will change their public key, and there's no record of the old public keys. And so we actually realized that as we were verifying these old emails and old email leaks, for instance, this is like Hillary Clinton's advisor's email inbox from 2016, and we went in and we ran the DKIM verification on all of them, and the red ones are the ones that no longer fail, that currently fail because we don't have access to those public keys anymore. And so only the green ones are ones for which we have those public keys somewhere, or those keys have not rotated for whatever reason. And so this is not great because this means now old emails you can't verify anymore. And so what we did is we basically put up this archive in which we're archiving all these old public keys as time continues. And so for instance, this is for Venmo.com. So we basically need this value called a selector, which is kind of in the received email from Venmo. It says, look, we're going to give you this massive random combination of 50 characters, and if you go to that lcwcy whatever domainkey.venmo.com, you can now get the RSA public key for Venmo. And if you go to s1.domainkey.venmo.com, you can get this specific email key that they probably use for some other kind of email. And so we kind of did this scrape on like the Alexa top million domains and a bunch of email inboxes, and we published all these keys. And so now you can query this like massive database if you go to archive.prove.email. But still, we've not solved the problem of how do you get old keys? Like, how do I get a key from 2013 or 2016 or something before we ever thought about making this website? And it turns out there's a really nifty way you can recover these lost public keys by manipulating some of the like math in RSA. And so this slide specifically is going to get like a little more technical because I'm going to like go into how we like do this reverse engineering. But the idea is that so an RSA signature is the idea that if I have this, and if you're not familiar with modular arithmetic, feel free to kind of tune out for this slide and then come in on the next slide. It's totally fine. So if you have an RSA signature, which is basically that DKIM signature, you're basically saying message to the power of this value d mod your public key is this signature. And so now anybody can go in and take it to the power of 65537. And if that matches the original message mod your public key, then that signature verifies. This is like concretely what is happening in RSA signature verification. And so you can imagine what I can do is I can take two signatures, M1 to the D mod n, M2 to the D mod n. And if I actually do this exponentiation, I write out what they are, I can now get kind of M1, and I can verify, okay, these signatures passed. And now if you write out, what exactly is modular arithmetic? It's just the idea that you added some multiple of that modulus to this value and you got that value. And so you just figure out what that value is. So you kind of say, okay, we're going to figure out what that modulus value is. And so great, so now we're going to subtract and we're going to get these two values. And then just from subtracting the signature from the original message and then taking the GCD of those values, you can now reverse engineer what the public key probably was. And you have to remove some of the small prime factors that might come from the GCD. But the idea is that this basically allows you to get those old public keys. And so we ran this whole scrape on a bunch of inboxes, and we were able to rederive these old public keys. And so now we have even keys from like 2017 or whatever that nobody's ever seen before. And now this allows like lawyers or whoever looking at these emails to be able to verify old emails. And one useful thing that we would love if folks could contribute is these selectors are kind of random values. Like we saw in Venmo, this is like this random hash string. And so there's no way to get this public key until we know this public hash string, meaning somebody has to have received an email from Venmo for us to know this selector string. And so to collect those selector strings, we let folks basically either collect their email or calculate offline, and then we basically scrape the selectors and then put that in a cron job that we keep hitting over time to keep archiving that key over time and then telling us when it changes. And so if folks like go here and then contribute those selectors, this allows us to archive more and more different emails, which would be super useful. And we had this big blog post where we explain like what we did with this archive, and there's a cool thing where you can kind of run this like batch GCD thing and hack like old RSA public keys if they used insecure randomness generation. But we actually verified all 1 million keys on the archive. Like we're not generated with insecure randomness, and there's no like random private key that you can rederive, which is quite cool. Cool. Okay, so now that we've gone over like broadly what the primitive is, some use cases, I'll talk about the future. So kind of some more use cases and how you can see this in the broader context of signatures, cryptography, and relating. So one example of things we've seen folks use this for, and I'll kind of lead into how we do decentralized OAuth with that, is people have done this to do smart contracts. So you can basically use emails to confirm transactions, which is not something we initially thought would be easy, but it turns out it's like a kind of a very good use case, and so you can approve transactions by just responding to an email. You can log in via responding to an email, which I'll kind of explain how exactly that works and how you can build decentralized OAuth, and you can recover your account by basically using your email as a guardian. Okay, so concretely, how can you have like decentralized login? This kind of seems like odd, right? Like when you're logging into a website with your email, like you have to have a Google OAuth thing pop up, and then Google verifies you logged in. But what we can do is we can basically say we can have people generate ZK proofs proving they responded to a login email, and have that authorize ephemeral keys. And this is quite interesting because many systems that we currently think about or rely on, like Blue Sky's AT or any end-to-end encrypted messaging service, relies on the user having some sort of public-private key pair that they authenticate belongs to them. And so now you can kind of imagine that maybe we can build a system in which you authenticate some key belongs to you by responding to some email, and then we collect that ZK proof, and now you can have this kind of decentralized login system. And you can have like scopes to avoid unilateral control over the account. So maybe a user can log in and say, look, I want to log into my, I don't know, my end-to-end encrypted messaging key on this website, but I don't want to share all of my chats or chat with anybody. I just want to chat with this one person because I don't trust this website very much. And so you can kind of imagine on the website, in just one line, they can just set up, look, I want to log in this email address with this username and allow some scope. The scope can be, maybe access to some sort of post or some sort of DM or a specific kind of encryption or whatever it is. And then you'll get basically an email, which is like, do you want to sign in on that account for this specific scope? You reply confirm, and then now you've signed in. And the idea is that you're now verifying the user's email service directly. So maybe the user has a Proton Mail email or something, and they respond to the email, now they've signed in. But you've never had to have like an intermediary between Proton Mail and the website to verify they logged in. You're directly verifying their signature from their Proton Mail account. And so that's quite cool because this means you can kind of build login in a totally decentralized fashion, which is something we've not yet seen on kind of existing decentralized protocols. Sweet. Okay, so kind of broadening the scope, we've spent this whole talk talking about emails. But it turns out that the only specific thing that was interesting about emails that let us do these ZK email proofs was the fact that there was a signature on it. And it turns out there's signatures in lots of other things. There's signatures in, for instance, your passport. Like almost all passports have a digital signature in them. So what you can do is you can do the exact same selective disclosure thing where you can tap your phone onto your passport, scan that NFC chip, take that signature out, and then do selective disclosure. So now I can prove that, say I'm over 18, but I don't reveal exactly who I am. Or I prove I'm an American citizen, but I don't reveal exactly which one I am. And we've seen folks use these exact passport proofs to run shadow elections, both in Russia and the US and other places, which has been quite interesting. And they use precisely this technology of ZK proof of passport signatures. There's tons of other signatures, DNSSEC, SXG RFC 9421 is kind of website front end, so you can now verify website front end and say, oh, here was some data on the front end. You can verify some Git commits, so you can say, oh, like somebody contributed to some GitHub repo. DocuSign, many documents you sign are also like actually digitally signed. So DocuSign will put like a digital signature on it. You can also verify that and prove you signed some legal document. Credit card transactions, I mean, this list is quite long. And you can imagine, though, that not all data in the world is signed with these signatures. Some data is not. So for instance, when you're using HTTPS or TLS, that data is not signed. Okay, it's a totally symmetric encryption scheme that's happening when you're doing that. And so for that, you have to kind of rely on some notary. So people will put like a third-party notary or proxy in the middle. And then the notary or proxy verifies, oh, some data went some way. And now you can use those proofs, allowing you to get all of that web data, but at the risk of saying, oh, we now have to trust that that machine in the middle didn't collude with any of the parties in the process. You can have something like a proxy, which allows you to do this very fast, but gives you effectively no cryptographic security on that kind of verification. But the point is, based on the amount of security you want, if you want very high security, you can do something with the ZK signature proofs. If you want slightly lower security, or other ways, attack vectors, you can use different methods which might actually be easier for some users to use, for instance. And this is the Passport website where you can do the passport scanning and do the selective disclosure. Sweet. Another thing I want to discuss is that the ZK email organization that we have is totally open source. Like everything we have is completely open source. All the repos, all the cryptography, anyone can self-host anything, which is quite interesting because we often will have people contribute like random ideas. They're like, oh, I think you can make this kind of proof, and they'll go make it, and they'll fork the repo, and they'll do whatever they want. And so it's been really curious to see how development in a totally open source way for extremely niche cryptography has actually led to a lot of interesting contributions. So maybe the thing I want to leave off on is kind of what exactly is like kind of cryptographic coziness. It's the idea that you can smuggle out your data from these Web2 services that own it by hijacking their signatures and then proving and selectively disclosing that data to whoever you want to prove to. And so you can kind of re-own your data and now selectively prove it without that third-party website being in the middle. You can build peer-to-peer services where you don't have to trust necessarily what these decentralized nodes are telling you. They can serve ZK proofs showing that, yep, that thing is honest, that person attested this way, whatever it is. You no longer have to trust those nodes as heavily. And you can keep privacy. By having selective disclosure, you can reveal exactly what you want to the different parties you want to based on how much you trust or don't trust them. And it turns out that on the side, we can also verify old email leaks, which is kind of fun. Sweet. And so if you want to contact me, I'm on Twitter and everything else at Aayush_G. And you can see more about the ZK email project over there at our homepage. So yeah, thank you for listening, and I will take any further questions now as well. Woo!
I guess in order to understand or like imagine potential use cases, could you just give us a very rough idea of the kind of runtime to construct a proof like that, like from any of the examples you've shown?
Yeah, it's a good question. So the runtime depends on kind of whether you're doing it client side or server side. So if you're doing it client side, which is what you might want if you want privacy for any of this, those runtimes, we're kind of working with some folks to build new systems right now, and those runtimes are ranging from like between like 10 seconds for a really small one to like maybe 30 to 60 seconds for the bigger ones. And kind of the legacy proving system we were using took maybe like 5 to 6 minutes. On the server side, this is extremely fast. On the server side, because you can throw GPUs at it, you can make it consistently like sub 10 seconds, or for large proofs, like sub 30 seconds for like really, really big ones. And so it's kind of, it sort of really depends where you are. And then if you really want to turbocharge it, like if you want to do like say the JWT proof really fast on a server, you could even get that like sub like 5 seconds. And I kind of expect these things to get faster over time. Like for instance, from 2 years ago to now, we already saw like basically a 10x speed up, and I expect that over time, you need to see 10 to 100x speed ups. And so right now, yeah, these proofs take 10 to 30 seconds, but I expect 2 years from now these will be sub-second. Sweet. I think there were some more questions. Yeah.
Yeah, this looks super cool. So what does the user need to actually do to get an email they received proved, do the selective disclosure? Do they have to take the plain text email apart, or can they just forward the email or something?
Yeah, so it's a great question. So how do you actually get these proofs working? Like, what is the user flow of doing this? So the one I showed on stage was basically, I logged in with my inbox. It looked at my emails to see which ones could possibly correctly be proved by the circuit. And then I just clicked it and clicked prove. But this requires this website to have access then to my inbox, which is kind of yikes. Most people don't generally say, surprisingly, you'd expect most people to not say yes to this, but in reality, like for instance, for ZK P2P, the one where you do the Venmo on-ramping, like 80% of users were fine just sharing their whole inbox and letting us scrape it to see where the Venmo email was. And we didn't, obviously, like the code is all open source, so you could self-host it and do it yourself. But the reason they probably felt secure is because you don't need to log in. You can upload the file directly. So I can go, for instance, to my inbox. I can say here, I can go to the email, and I can say like, show original or download message. And if I click download message, it'll download that message as this .eml up here. And then I can just upload this .eml directly to this website. So I can just hit choose file, select the .eml, and now that is enough for me to make a proof. So it's kind of, do you choose the like very easy user flow with not great privacy guarantees, or the slightly harder user flow with very good privacy guarantees? And so we think that by just making it possible to do both, you've also made yourself more trustworthy on the first one, because now people are like, oh, I know that if I want to do the private way, I can exit, and so okay, I'm willing to trust them a little bit more. And so historically, we've seen that just the existence of the second option is enough to convince people to often do the first one. But it's important to have that second option. Yeah, but it's a good question, like how exactly are people making these proofs?
So if you're like relying on the email contents for like verifying or like proving any sort of statement, then like you're kind of relying like on the email contents, right? Like also like if you want to build like some larger application thing like around this, like you're relying on the email contents kind of staying fixed. Like it's sort of an like implicit API that you're using, right? And usually companies like don't care at all like about like versioning their email templates or anything like that. Is there like, have you thought about that like in any way? And like, is there like any work around that? Like also kind of tracking changes, how like companies change their email template over time, and like how do you then deal with that? Like I gotta verify like some email that was sent before this date where like, I don't know, they rolled out some new thing. Like it's not super interesting technically, I guess, like solving this stuff, but feels like an obstacle to like actual adoption, like in broader.
Yeah, it's a good question. Like, how do we adapt to emails changing their email template, and then us still being able to make ZK proofs of that? So yeah, there's kind of there's like a few ways we think about this. So one is that yes, email providers will change their email template and they won't version that at all. And sometimes that'll break the flow. So for instance, like the Venmo flow was broken for some time because the email has changed and now no longer has the information we need to parse it. But as long as the email is still provable or still has interesting content, the idea is that like having a system like this in which you can kind of you can just submit a new pattern and define this thing quite fast in just like a couple of forms. Like basically making it very easy to change how you actually parse this email template allows people to react very fast to changes. So for instance, here you can just go in and edit and say, oh, now the ticket format has changed, the subject looks slightly different. I can go in, edit it, change one of the words, and a new proofs type will recompile, an hour later or something, and now we have a whole new proof way to do that. And so the idea is that as long as you make the system fast to update and reactive, you can often adapt to these changes in email templates very fast. You can also imagine that for versions like the whistleblowing case, this is like totally agnostic to the structure of the email. Right? The email can change as much as it wants over time, and the user's still going to go in and use a little highlighter and redact the stuff they don't want to reveal. And so that's completely robust to the emails kind of changing over time. And so, yeah, it's a good question. Like the email, like because emails are not versioned very well, it's kind of annoying. People will change it. But the nice thing is they have to be pursuant to the spec. They have to do this SHA-56 and this RSA signature correctly, or else spam filters on the other side will always reject their emails. And so at least we know that it is possible to verify the email. The question is just like how fast can we react to the parsing? Yeah, but it's a great question. And then one thing also I forgot to mention on the previous question for this this proving is that all of this pulling of the emails happens entirely client side. Like when you do the login with the email and you go through the emails, that whole thing happens on the client side. We have the like OAuth key, everything on the client side, and all that is done there. So we keep none of that data. Yeah, sorry, just a point on that. Cool. Thanks for the questions though.
Just a quick question. So you mentioned that you have this public key archive,
Yep.
old public keys. I mean, how do we know to trust the archive?
Yeah, so it's this kind of annoying situation in which, like, this sort of thing has no signatures on it, right? The thing that gives trust is if we could prove, oh yeah, there's a signature showing that this thing is correct, and we at this point we sort of like don't, and so the best you can do right now is to get like a DNS, and we have like this big like blog post about it, but if you're lucky, so for instance, Proton Mail turned on this thing called DNSSEC, in which Proton Mail themselves signs their own public key on DNS, and you can verify this chain of signatures up to Proton Mail's like ICANN domain root. And if you have that DNS signature, then you're totally set. The DNSSEC will allow you to verify that whole thing, and there's no trust on the archive. But for a case that we don't have this, you're sort of stuck trusting like either a centralized provider like our DKIM archive, or ideally we want to like decentralize it. So we have like a bunch of notaries all get all of these keys, and they all fetch them and they say, yep, like this looks correct, and then we have some sort of economic security or some sort of consensus on this. But it's a messy system, and we have this like in the blog post where we describe the archive. We like go over like yeah, like, you know, why is it not decentralized? How can we decentralize it? What are ways? And I'm excited for folks to contribute. Like, I think this is a very compelling system, and it's like you can plug in a lot of kind of existing decentralized tech and be able to get at least some sort of consensus on it, even if it's not cryptographically perfect. Of course, yeah. Yep. Yeah, and so if you're lucky and the email's recent and the DKIM key is not rotated, then you yourself can go fetch the key and be like, yeah, that's the current key. But if you're not lucky enough for that to be the case, yeah, you're going to have to trust some sort of like historical archive in this case. And one thing we do to slightly reduce the trust assumptions, doesn't actually do anything, but it's like we'll timestamp it when we fetch it. So at least you have a timestamp of, oh, like I hit the API and they didn't just make up something today. They like sent me, here's a timestamp showing it was committed to some chain like 3 months ago or whatever. So at least we have that kind of thing, but it's not a lot. Yeah, it's a fair point. Well, I don't know if we have more time for questions or if we should move to the next talk or.
Cryptographers go talk to cryptographers.
Okay, fair enough.
Cozy, cryptographic coziness, really great. Like this is a great example. Cryptography is math and is in many ways a low-level primitives. Well, a lot of the things that we're building rely on, whether we know it or not, including the modern web. So really appreciate you walking us through that. It was great. Thank you very much.
Thank you.